Hello everyone, I'm Neura, and in this video, we're going to explore a really practical machine learning project for cultivation analytics. The big question is this: what if AI could catch watering problems before they damage your plants? In this project, we are building a classification model that predicts whether a plant may be underwatered, healthy, or overwatered based on environmental and plant condition data. And what makes this project interesting is that watering issues are not always obvious. A droopy plant might need water, but it might also be suffering from too much water. That means a grower can't always trust one signal by itself. This is exactly where machine learning becomes useful, because instead of looking at one number in isolation, it can learn patterns across multiple signals at the same time. We start by importing the core Python libraries for the project. We use pandas and NumPy for working with the data, matplotlib for visualization, and scikit-learn for the machine learning workflow. We also set a random seed so that our results are reproducible. That means when we run the notebook again, we can get the same synthetic dataset and the same model behavior. This is especially helpful when building educational demos, because it keeps the lesson stable and easy to follow. Next, we create a synthetic but realistic dataset. This is one of the most important parts of the project. Since we are not using real cultivation sensor logs here, we generate examples that represent 3 plant conditions: underwatered, healthy, and overwatered. Each class is built with environmental and behavioral signals that make sense in context. For example, underwatered plants tend to have lower soil moisture, more days since the last watering, and stronger leaf droop. Overwatered plants tend to have high soil moisture, very recent watering, and a positive pot weight change because the pot is staying heavy. We also include temperature, humidity, and runoff EC to make the model more realistic and give it more context to work with. After creating the dataset, we preview it and look at summary statistics. This is a very important habit in machine learning. We check the first few rows and confirm that the values make sense. We also look at the class counts to verify that the dataset is balanced across all 3 categories. Then we plot the class distribution. This gives us a quick visual confirmation that the dataset is balanced. Balanced data does not automatically guarantee a good model, but it helps us avoid one very common issue where a model performs well only because one class dominates the dataset. Now we encode the target labels. Machine learning models work best when the target is numeric, so we map underwatered to 0, healthy to 1, and overwatered to 2. Next, we define our features and target. Our feature columns include soil moisture, temperature, humidity, leaf droop, and pot weight change. The target is the plant status label. We are teaching the model to recognize a combination of signals, and that is much closer to how real-world problem-solving works. After that, we split the data into training and testing sets. The training set is what the model learns from, and the test set is what we use to evaluate how well it performs on data it has not seen before. Now we train the random forest classifier. A random forest is a collection of many decision trees working together. Each tree looks at the data in a slightly different way, and then the forest votes on the final answer. This makes it a great model for tabular data like this. It can learn that low moisture combined with strong droop and a lighter pot points strongly toward underwatering. Once the model is trained, we generate predictions and calculate accuracy. In this notebook, the result comes out extremely high, even hitting 100% on the test data. At first glance, that sounds amazing, but this is actually a great teaching moment. A perfect score on synthetic data does not mean we built a perfect real-world model. It really tells us is that our generated dataset is very clean and structured. Real cultivation data would be messier and more difficult to classify. The classification report gives us a more detailed breakdown. It shows precision, recall, and F1 score for each class. The confusion matrix gives us a visual view of the same result. All predictions fall on the diagonal, which means every example was classified correctly. Next, we look at feature importance. This helps us understand which signals mattered most to the model. Feature importance is one of the most useful parts of a project, because it moves the model from being a black box into something more interpretable. Finally, we make live prediction examples. We feed in sample plant conditions and let the model predict the status. This is the kind of simple decision support idea that can eventually become part of a larger smart grow system. To finish up, we print the predictions in a clean, easy-to-read format. And this is a great place to wrap the lesson. Machine learning can help identify watering stress, but the quality of the model depends on the quality and realism of the data. In the real world, we would want sensor noise, borderline cases, and actual cultivation logs to make the model more robust. But as a proof of concept, this is a strong example. Thanks for watching, and I'll see you in the next project.